In this lesson, we're going to look at applications of quadratic functions. So it's just a couple of examples. Example 1, example 2. Let's see how they play out. A water balloon is catapulted into the air from the top of a building. The height, h at t in meters, of the balloon after t seconds is given by this function right here. H at t equals negative 5t squared plus 30t plus 10. And then we have the questions: what was the initial height of the building? When will the balloon reach a height of 30 meters? When will the balloon hit the ground? So these are all things that we can figure out with the, from the function. So it's always nice to draw a picture as we go along, if possible. So I'm going to do that. But let's actually take what we have in order here. What was the initial height of the building? I can actually answer that part without a picture, and then I'll add it to the picture after I get it. But there's a couple ways of thinking about it. First of all, we know that this value here, when this is a quadratic in standard form, the form y equals ax squared plus bx plus c, we know that the c value is our y-intercept. But in case you'd forgotten that, we could prove that using the function. So the y-intercept, well, in this case, let's actually start by putting a Cartesian plane here. And I'm going to call this the t-axis instead of x. I'm going to call this the h-axis because time is my independent variable, height is my dependent variable. And as far as this function goes, obviously it starts at time 0, right? The initial height is when the time equals 0, which means that I want to find h at 0. If I put 0 into this function, then it's pretty obvious that what happens is that all the terms go away except for the last term, which is why my initial height is 10 meters. So in terms of this question, I don't have a scale on this, but let's pretend that this is 10 here. I'll choose that to be a height of 10. So that's my y-intercept, or my h-intercept in this case. So that's my starting point. And then if I were to graph the function, being a quadratic, unless we started at the vertex, which I don't believe we did. I mean, usually these questions don't generally start at the vertex. We can assume it's going to go up for a little bit of time, and then it's going to come back down, and it's going to hit the ground at some point, right? So the t-axis, the x-axis, is going to represent a height of 0, which would be the ground. So we don't even really need any of these other quadrants here. Everything we're doing is in quadrant 1. So anyway, there's my answer to part A. I've got the height of the building. And then for part B, when will the balloon reach a height of 30 meters? Oh my goodness, that is I guess I did not draw that quite as to scale, did I? Let's change things a little bit. Oh dear, I took away too much. Let me take away a bit more. I just want to make it so it's a nice scale drawing. All I'm going to do is I'm going to put my 10 a little lower. I didn't realize it was going to go so high. So let's say 10's here instead. So it's being catapulted, so it's going to go up quite high. Okay, so everything else is the same. And it's going to come down. I don't know how high it's going to go, but I assume it's going to go at least 30 meters since the question asked for that. So let's just say that 30 is about here. Okay? So when is it going to get to be 30 meters? Well, if you think about it, assuming that 30 isn't the vertex, it's going to hit 30 meters at 2 different times. It's going to hit 30 meters on the way up and on the way back down. As far as the equation goes, B part is asking me to find t when h at t equals 30. And we know that h at t is just the y value. So it's like putting 30 in for the y value in this function. So I'll put 30 in on the h of t on the left side. Have the equation 5t squared plus 30t plus 10. And then I can solve this equation by rearranging, putting it back in standard form. So I'll subtract 30 from each side, giving me 0 on the left side. And if I subtract 30 from the right side, 10 minus 30 gives me negative 20. So there is my new simplified equation. And if I solve this equation, I will get the values for the points where the height is 30. So solving, we should always try to factor first. And when we factor, we always start with common factoring. So I see I can take a negative 5 out of each term. So I've got t squared minus 6t plus 4 when I divide each term by negative 5. Now, sadly for me, what I've got left in the brackets here does not look factorable. I can't think of any numbers. They're going to multiply to give 4 and add to give negative 6. So that means I have to rely on another way of solving it, and that would be the quadratic formula in this case. So t is equal to negative b, negative b plus or minus the square root of b squared minus 4ac. Put that all over 2a. Well, what's a, b, and c? Well, a is 1, b is negative 6, and c is 4. Again, that's just pulled out of the equation here, right? And plugging those numbers in, negative 6 is going to be a positive 6. Negative 6 squared is going to be positive 36. Oops, that should be a minus 4, though. Times 1 times 4. Okay, all over 2 times 1. So 6 plus or minus the square root of 36 minus 16 all over 2. And 36 minus 16 is just 20. So 6 plus the square root of 20. 6 plus the square root of 20 is 10.47. And then I can divide that answer by 2. And I got 5.2. Let's round it to 1 decimal place. So 5.2 seconds. And if I subtract, then what I'll get is t is equal to 6 minus the square root of 20. Clear this. 6 minus the square root of 20, which equals 1. It does equal that, but then I have to divide it by 2. And that equals 0.8 seconds, again, to 1 decimal place. So it turns out that there's 2 solutions, and we expected that. Again, that's where the sketches come in handy. They let us see that we can expect 2 different solutions. So we have one solution here at 0.8 seconds. We have another solution here at 5.2 seconds. So there are my solutions for part B. When will the balloon hit the ground? So that means that we're looking for one of the zeros, right? So I can go back to my original function, which was h at t equals negative 5t. What happened there? Negative 5t squared plus 30t plus 10. And then set 0 in for h of t because the height would be 0, right? When it hits the ground, h of t equals 0. So again, just substitute 0 in, and then I need to solve this equation. Again, I'll start out by common factoring if possible, and I can. It is possible. I can take out negative 5, and I got negative 6t again, and I've got negative 2. And again, sadly for me, it does not look factorable, so I'm going to have to go back to the quadratic formula. So let's just jump in. Negative 6 plus or minus the square root, negative 6 squared minus 4 times a, which is 1, times c, which is negative 2 this time, all over 2 times 1. And that's going to be 6 plus or minus the square root of 36 plus 8 all over 2. 6 plus or minus the square root of 44 all over 2. Okay, so if I use the plus square root of 44, then 6 plus square root 44, take that, divide it by 2, 6.3 seconds. That's one of my answers. And in fact, when you think about it, there really only should be one answer, right? So this would be 6.3, and that fits in with what I've already got. So what am I going to get from this? Well, let's see. If I put a negative, if I do 6 minus the square root of 44, and then divide my answer by 2, I get negative 0.3. So negative 0.3. Well, we know that we're starting at time 0, so negative 0.3 makes no sense. I mean, it makes sense, the quadratic pumped it out, but it doesn't make sense in the context of this question. This negative 0.3 would be if I were to continue this parabola backwards, then I would have had to start negative 0.3 here, but that doesn't fit into the context of our question. It can't land 0.3 seconds before it was launched. So that we'll call this an extraneous root, and we will disregard it. All right, what else do we have? A rectangular field with an area of 8,000 square meters is enclosed by 400 meters of fencing. Determine the dimensions of the field to the nearest tenth of a meter. All right, so again, sketch. That could be really helpful, couldn't it? So rectangle. Oops, that was supposed to be a rectangle, I thought. There we go. So what do we know about this field? We know the area is 8,000 square meters. We know that it has a length, and, although I probably call this side the length, and a width, and that the perimeter is 400 meters squared. So the perimeter, of course, is 2 times the width plus 2 times the length. And if I were to substitute this perimeter of 400 meters, we also know the perimeter is 400 meters. Then I can substitute that into here, and I get 400 equals 2W plus 2L. So that's just an equation, obviously. And I can isolate it in terms of L or W, which I think will do. So maybe, let's say I try to get W by itself. So if I bring the 2L to the other side, I'd have negative 2L plus 400 equals 2W. And if I divide each side by 2, I'd have negative L plus 200 equals W. And then I could just, I like to have my isolated variable on the left, so I'll just flop sides there. And so W equals negative L plus 200. So that is an equation I can work with. I've got 2 variables in a single equation. At this point, you probably recognize that I can't solve a single equation with 2 variables in it. I need a second equation with those same variables that allow me to solve it. That's where the area comes in. Area is also equal to 8,000, as we saw just above. but it's also equal to length times width, right? So if I put 8,000, sorry, I'm not sure why my Apple Pencil is really going wonky today, but I have to keep erasing strange things it writes. Anyway, I'll put the 8,000 in for A, and so I got A equals L times W. That is another equation. So this is my system of equations, and we know that we can solve a system of equations, any kind of system, if we got two equations with two unknowns. I could use substitution. So I'm going to call this equation 1, and I'm going to call this equation 2, and I'm going to substitute equation 1 into equation 2. When I do that, I'll have 8,000 equals L times negative L plus 200. So I took this and substituted it in for W in equation 2, right? So that's how substitution works. I can expand it out and simplify it. I can do the distributive law. I can bring this 8,000 to the other side. So let's do that. And that's the second step. So I'll leave the 8,000 on the left for now. But if I expand, I get negative L squared plus 200L. Now if I bring the 8,000, actually I'm going to leave the 8,000 where it is. I'm going to bring the right side over to the left. That'll get rid of that negative. So then I'll have positive L squared minus 200L plus 8,000 equals 0. And we recognize that's a quadratic. And if I can solve this quadratic, that would be good. So two things are going to multiply to give 8,000 and add to give 200. Nothing's popping to mind immediately. I'm assuming it's probably factorable. But since I'm not seeing the answers, I'm going to, again, go to my old friend, the quadratic formula. So in this case, it's L that I'm solving for. So L is going to equal, and I got A is 1, right? The coefficient of squared term. B is negative 200. And C is 8,000. So 1, negative 200, 8,000. So plug that in. So negative 200 plus or minus the square root of negative 200 squared minus 4 times A, which was 1, times C, which was 8,000, all over 2 times A. So positive 200 plus or minus the square root of, I guess, 40,000 minus 4 times 8,000, which would be 32,000, all over 2. So 2,000 plus or minus the square root of 8,000. Well, maybe this one isn't factorable because 8,000 is not a perfect square. So let's get our two different answers again, right? So for one of the, when I do a plus, 200, it was 200, right? 200, oh, I added an extra 0 here. I thought it was 200. 200 plus the square root of 8,000. And then I take this, take that answer and divide it by 2. And I got 144.7. 144.7 meters. If I do the negative one, since that's positive, I'm going to go ahead and guess that that's my only answer. I'm going to assume that if I subtract, I'm going to end up with a negative answer, but let's, just confirm that for the sake of doing our due diligence. 200 minus the square root of 8,000. No, I take that back. We did not get a negative, but actually I know what that means. That will be my width. Now that I think about it, 55.3. So 55.3. I know it's called the length, but it's given me actually both solutions. As we'll see, I'll explain in a second in case you don't know what I mean. But either one of those would work for the length. Now, by convention, we call our longer side the length. So let's say that we take this one here as our length. Right, so length is 144.7. Remember, we can always get our other value by plugging it into one of our equations. So let's say I plug it into equation 1. So I'm going to sub L equals 144.7 into equation 1. And what I'd get is W equals negative 144.7 plus 200. And guess what that equals? Well, that equals 55.3. And so that's going to be my width, which is, matches what I've got up above, just that it was called length up above. But those are the two dimensions. So the length has to be 144.7. The width has to be 55.3. If I add those together, then I get 200. 200 times 2 will give me my 400 meters of fencing. And if I multiply them together, it should give me my 8,000 square meters. So 55.3 times 144.7. And as you can see, it's not exactly 8,000, it's 8,001.91, but that's only because we rounded it. If we carried more decimal places, it would have been closer to 8,000. So there's our answer for that one.